Hi, I would like to welcome on this live session on discussion on black hole. So, one of the most mysterious and exciting object in the universe. Um, so, we can begin from the classical definition of black holes, and then we then can go to the Einstein's theory, general relativity theory. What is black hole in terms of the Einstein's general relativity of theory, and then we can move to quantum mechanical interpretation, the quantum mechanics side of the black hole, uh, and we can also talk about some of the exotic idea about black holes, something like such as or other forms of black hole like white hole or wormhole. So it's going to be a really exciting ride. So please do not hesitate to post your comments or questions. Um, I will try to answer. Um, so beginning from a brief history of black holes. Um, Today the first idea of black hole is credited to John Michel in 18th century. He was a priest, a clergyman actually, and natural philosopher who was also an astronomer. So his idea was that there could be some dark stars. He didn't call them black hole, but dark stars. Um, there could be some of the dark stars which has so much gravity in them that the light may not escape from them. So if that is the case, then you wouldn't be able to see. That's why it's a dark star. So that's the classical idea or interpretation of black hole, which started with. So classically, to make black hole, you basically need two concepts. One is the mass and gravity, basically the gravity with mass, and the other thing is escape velocity. Escape velocity is the velocity on any surface of a mass, like a planet, something. If you project or throw something with this escape velocity from a planet or star, then it will never come back. So that's the idea of escape velocity. So if you throw something uh, um, with an escape velocity, it will never come back. Sorry. So and what happens the if the planet or star is so dense that uh, even if you throw something with speed of light, it will not it will not escape, meaning it will be trapped inside the deep potential well of the gravity. So this was the first idea uh, proposed by John Michel. This idea is still based on Newton's law, classical theory of gravity. Um, and then, but the natural expansion, the natural idea behind the black hole uh, comes from the relativity, of which is fairly recent idea. Excuse me. I see people still coming, so maybe we can wait for a few minutes till people come and so We will, as mentioned, we will uh, talk about these general relativistic version of the black hole, the natural interpretation of black holes. Um, so, in general relativity, the black holes are natural outcome of the Einstein's solution of Einstein's equations. Um, so, what happens that the first of such solution was actually solved by the Karl Schwarzschild, um, who was a German soldier also. Um, he what he found was a spherically symmetric solution of the black hole, uh, and this was actually the first theoretical idea behind the black hole. I think I should probably wait for people to come. We will shortly begin when people enough people come. Uh, um, so we can begin and black hole discussions, um, starting from Newtonian concept of black hole to the Einsteinian general relativity uh, version of the black holes, and then we can move to quantum mechanics, uh, the Hawking radiations kind of thing, and slowly we can then move to the uh, more exotic ideas in physics, similar to black holes, can be white hole or wormhole, things like that. Um, so as I was saying, the uh, uh, the black hole, the natural way of getting black hole is Einstein's equations. Um, there is a qualitative difference between the Newtonian and uh, the Einstein's theory of gravitation. Uh, in, in Newton's idea of gravitation, there is a force of gravitation between 2 points, between two masses, and because of that, the one body, like the sun, uh, or the planet goes around the sun, um, but there is a force. Now, Newton himself was not comfortable with the idea of action at a distance. Like there was no answer. How does the force of gravity propagates uh, between two masses? So he was not comfortable with these ideas. So, nevertheless, there's a force between two masses. But in Einstein's theory of relativity, things are different. The mass the mass curves the space-time fabric, and creates a curvature, and in that curvature, the planets or the other masses make a natural orbit. So so in Newtonian mechanics, uh, there's a force between two masses, but in Einstein's uh, interpretation of gravitation, the 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 presence of mass curbs the fabric of space and time, and so that the planets follow a natural motion. So there is no force in Einstein's theory of general relativity. Um, so now the idea of black hole, basically, which was first solutions of spherically symmetric equations of Einstein, was done by um, Karl Schwarzschild, a German astrophysicist, um, who solved this equation and um, proposed the possibility of event horizon, beyond which the time was there would be a timelessness, and uh, so when this test particle crosses the event horizon, then there would be no information about this test particle. So that was the idea of the Carl Schwarzschild, who proposed. Um, well, at the time, even Einstein was not sure about the idea of black hole, um, because uh, the solutions of Einstein's equation would basically have many forms of the solutions, and this was the first kind of solution that was proposed by Schwarzschild. Um, and then were there are many implications of this um, Schwarzschild black hole, spherically symmetric, that the time would slow down uh, near the event horizon. Again, the event horizon is a surface uh, beyond which the singularity heights. The singularity means the infinite um, density of uh, the matter. The question is that black hole is a uh, the dense the most dense or densest form of the matter. Um, so so what is the density of black hole? That is not very much clear. Um, the stellar black holes mainly arise from the during the evolution of the stars. Um, you might have knowledge about the evolutions of stars. Uh, stars stars from the clump of coal gas. Uh, the it starts slowly contracting under the influence of the gravity, and uh, and slowly contracts and contracts and getting denser and denser, and at some point of time it becomes so dense that the pressure increases, the temperature increases, and slowly at some point of time they start nuclear fusion. Yeah, and this is the birth of a star, actually. The moment uh, nuclear fusion starts, a star is born, and then begins the life of a star. A lot of stars spends most of its time in during something called main sequence. Um, it outputs. It's fairly stable. It outputs tremendous amount of energy into the space, and but after some time, uh, the outer. So depending upon the mass of the star, it takes the fate of a star is takes a different routes. Um, for a medium-sized star like a sun, after some time, uh, um, the hydrogen. So in previously in the beginning, the hydrogen fused to become helium, and then helium becomes to carbon, and higher forms of uh, matter are formed. But then later the outer boundary of the stars is cast away, blown away into space, uh, and it becomes redder and redder. Also, you must have heard about the some red giant. So if the sun were to be a red giant, it would swell up to the Earth. So the Venus, the Mercury, and these planets will be swallowed by the sun. So it will expand and become a red giant. And after some time, this outer layer would be cast into the space, and the core collapses and becomes a white dwarf. Uh, it further cannot contract. The gravity is very strong, but it cannot further contract because the mm, the gravitation is counterbalanced by the electron degeneracy pressure. That's what called. So basically, it's a quantum idea from quantum mechanics that no two electrons can be in the same state. So because of that, the gravity further cannot uh, uh, contract, uh, and then it becomes a white dwarf. And the white dwarfs are has very high temperature. They shine for some time and slowly they cool down. So, but if the mass of the star is greater than that, if the mass of the star is greater than that, then uh, the remnant star, so the outward layer of the star is blown away and into the space, and there's still sufficient amount of matter inside, and the gravity becomes so strong that the electron degeneracy pressure is not sufficient to hold the gravity. It further squeezes and become more denser, and then it becomes a neutron stars. So the neutron stars are so dense stars that one spoon of neutron stars are heavier than the entire Mount Everest. You can imagine how dense they are, and they are truly, in the sense, the like a diamond in the sky. They are truly even denser than the diamonds. They're actually the diamonds of the sky. Um, now, so the the gravity of neutron star is very strong, and the gravity wants to squeeze it further, but this time not the uh, electron degeneracy pressure, but the uh, neutron degeneracy pressure holds the gravity against the gravity. But then uh, it remains a neutron star, and the famous examples of the neutron stars are the pulsars, right? The pulsars are the cosmic clocks. So a neutron star is a dense matter. Also, it has got angular momentum. It spins very fast, and then it has a magnetic field, and it spins. So if a there's angle between the rotation of axis and magnetic field, and the jet is the strong jets coming, and this faces, this swipes in the sky, and it happens to pass through our line of sight, and that's where we see uh, the periodic profile in radio, mostly in radio. So they are like beacons of light in our galaxy, and there are thousands of them have been detected, and they have a magnetic field uh, 10 to the power 12 or 13 Gauss. You can compare the magnetic field our Earth is about 1 Gauss or less than that. So you can imagine how strong big magnetic field they are. So now, to form the black hole, if the mass of the remnant star after that outer layer is cast away is more than three or four solar mass, then the degeneracy pressure of neutron star is not able to stop the further squeeze of the gravity, and it collapses into singularity. So this is how the star black holes are formed. I would like to take a pause and say, wait for some comments, say hi or something. Okay, if there are any comments or questions about the stellar black holes. Okay. um, uh, these are the stellar black holes. There's a other types of black holes are supermassive black holes. Um, Supermassive black holes are are billions times the mass of the solar mass of the sun, and so now it is widely accepted that the every galaxies had supermassive black hole at their centers. Um, but the it is still mystery how how the supermassive black holes are formed, because like stars, the evolution of galaxies, that they also live in binaries, and the two galaxies over a long period of time merge. uh, Galaxies also live in three or four systems, and over time they merge and get bigger and bigger. The black hole at their centers becomes larger and larger over the period of time. um, but the James Wave Telescope can see universe, uh, early universe. In astronomy, the farther you look, the farther in distance you look, the further in time that's further in time. Um, um, okay, I see some of the comments here. Um, Ganeshi writes, so there is a singularity point in center of black hole. Uh, yes, that's right. So what is at the center of the black hole is as a big mystery, because it is singularity there, but this is hidden singularity. There's a concept of also the concept of naked singularity. So a singularity is would mean an infinite density of the matter. Um, so there are some ideas that at the center the density of the star is infinite, but this is not. People do not like this singularity, because it is something like we don't know what happens when you divide one by zero, kind of thing in infinite. So there are some other ideas that come from Planck, of quantum mechanics, maybe Planck star, that somehow there is finite density, not quite the infinite density of the star. So there are many approaches to look at the center of the uh, black hole. So at this point, we're not given to know to peer into the further into the event horizon, because nothing can escape from the from beyond um, event horizon. So we don't have much idea about what's in there. So that's why they are mysterious black holes. And Shreya, there's a question from Shreya Thamrakar. What is the future of our universe? Uh, this is actually an interesting question, Shreya. Um, so as you know that the universe is expanding and expanding. So how do you know it's expanding? Because the Hubble, yes, the Hubble looked into the that was long ago. Actually, Hubble was from 1900, when he looked at the galaxies. He found that the galaxies are receding from us. They're going farther from away. Not only that, the farther the galaxy, the faster it's moving. That's how the universe is expanding. And then um, recently we found that from the observations of supernova, the supernova are the distance, something called the uh, cosmic candles, meaning they will tell us the distance. So they're distance candles. So in 95, somewhere in that period, we detected some supernova, and that would tell that uh, the universe it's not only expanding, but it's also accelerating. When it's expanding and further expanding, but it's also accelerating the faster. It's expanding faster. That would mean that soon the outer parts of the galaxies will be traveling faster than light, and they will not be our part of universe, and the galaxies, the clusters will be moving away away from further from us, and slowly the universe will be very cold places to live. There will be nothing. There will be the remember with the expansion of the light, there's a redshift of light, meaning the lights like X-rays and gamma rays thin out to infrared, like CMBs. So there will be a very weak photons around, uh, and by the process of these star formations, there will be mostly brown dwarfs and black holes, mostly black hole. At the near end of the universe, there will be mostly black hole, and black hole will survive for a long time because black hole emit only by Hawking radiation, if you know what that is, and Hawking radiation is a very, very, very slow process, and so when these black holes will evaporate, there will be nothing, only the weak photon will be left out, and that is the current scenario of the fate of of the universe. Okay, that's very exciting and interesting a topic. People are still looking into it, what will happen, but of course the time scale is billions and billions, probably a Google year, but not now. uh, so we were into a black hole. So continue. Excuse me. uh, Ganesh Tripathi writes, is there a chance for time to stop in the center of black hole? Yes, yes, this is exactly the idea. So if you go get closer and closer to a black hole, the time very much slows down. And once at the event horizon, basically there's timelessness, meaning uh, inside the black hole the time wouldn't evolve, and this is exactly happens. The idea of event horizon actually comes from the timelessness, and yeah, this is right. This is the time will stop at the center of the black hole. Yeah, that's the idea. uh, and the black holes would now the quantum mechanical part is that um, in the beginning they were thought that black hole are just black, in the sense they do not emit light. But the Hawking, his famous work on Hawking radiation, uh, the idea was that the black holes may uh, emit emit in some sense. So how can they black hole emit? So this is now is popularly known as Hawking radiation. So according to the quantum mechanics, so he was actually to unite the general relativity and quantum mechanics. In quantum mechanics, the the vacuum is not actually vacuum. Uh, it is actually from vacuum constantly the virtual particles pop in and out of existence. So the virtual particles are created and annihilated, created and annihilated. That happens. That frequently happens. So that is the quantum mechanical definition of the vacuum. So it might have happened that if such pairs of particle and antiparticles are created at the border event horizon, then it may happen that one of the particle may fall into the black hole, and so, and to conserve the other quantities like momentum and energy, the other particles should go away from the black hole, and that's how the black hole emits. But it looks like the uh, uh, the intensity of that emission is very, very weak. So it takes, so as I said, the at the end of the universe, even the black holes evaporate away. But this time scale is very, very long, because uh, it takes long time uh, uh, for a black hole to evaporate through Hawking radiation. So that's the idea of the Hawking radiation. Um, so one of the other idea of the black hole in using quantum mechanics is that um, the there's something called black hole paradox. Uh, okay, this another question. How far is our universe from black hole? How far is our universe from black hole? Um, well, okay, probably I should have kind of talked about where are the black holes. So I think I mentioned that every galaxy has a black hole at their centers, meaning our galaxy Milky Way also has a supermassive black hole. That was one of the Nobel Prize of 2020. It's called Sagittarius A. They were just studying the motion of the very innermost stars at the core of our galaxies, and found that the mass should be very large, and that there was the existence of black holes. Okay, so again, once again, there are two kinds of, roughly speaking, there are two kinds of black holes: the stellar black holes and the supermassive black holes. The stellar black holes come from the death of the stars. They are all around in our galaxy. Okay, in binary systems. Uh, um, for example, Cygnus X1 is the famous black hole candidate, galactic black hole candidate. There are other ways to detect the black hole, but they are plenty of in our galaxy. The other types of black holes, which are supermassive black hole, are at the center of the galaxies. So, meaning there are billions of galaxies in the universe, and so which are, so at the heart of each galaxy is a supermassive black holes. So, how far is our universe in black hole? Our universe has a black hole inside it. Okay, so black holes are not in other universes. The black hole is actually in our universe, and they're everywhere. They're everywhere. So I hope that this answers Shreya Tambraka's question. Um, and so the other exotic idea in about black hole is that there's some paradox about black hole. The paradox is that, according to the quantum mechanics, the information never dies. So there's conservation of information. But when something falls in the black hole, the information is lost. Um, uh, the black hole doesn't care whether a book falls in it or a stone. It treats them equally. So, in some sense, black hole are the the delete history of anything. You don't know what when something falls into black hole, then it falls. You cannot tell it was a is a stone, or a book, or anything else. Now this is a bit inconsistent with the idea of uh, the conservation of information, because so according to the informations of the information theory, you should be track the history of any particle to the beginning of the universe and to the end of the universe. So you can take a simple example. If you say there's a paper and you write a letter, okay, there's a letters in a paper and you burn it. So so what happens when you burn a paper? It becomes ashes, goes around the. So if in some way, the paper is burned, there's nothing you cannot read the what was written in the. But in principle, if you were to track the amount of smoke and ash and then the things and analyze, you should be able to retrieve what was written in this paper. Okay, so that's very, the information never dies. You should be able to retrieve information. But when things fall into black hole, then that information is lost. So you can't get it. um, this is called black hole paradox, black hole information paradox. um, and one of the solution or proposed solution of this black hole paradox is that um, the the information of the black hole is not is stored into the surface of the black hole. Actually, there's something called entropy, yes, because as the black hole, um, its material, it grows bigger and bigger, and so does its outer surface, the surface. So one of the idea is that the information is not completely lost into the black hole, but it's encoded in the surface of the black hole because it grows with as it it's for the matter. So this is called a holographic principle, and this is one of the exotic ideas that the information of the volume or 3D volume of galaxy is actually encoded into 2D of the black hole, and this is one of the exciting ideas, but still theoretical ideas in black holes. Excuse me. Um, is so Ganesh Tripathi asks, is there a chance for the Sagittarius A to swallow our galaxy? Um, in principle, yes. I mean, if it's everything gets closer, the black hole can swallow everything, right? But the thing is that uh, the one of the property of the black hole is that its gravity is very intense, very close to black hole. If it's farther from black hole, it doesn't affect much. For example, um, let's say if the sun were to become black hole, okay, um, for any hypothetical reason, let's assume that the sun turns into black hole. Uh, then nothing would happen to us except for that we will not receive light, but the gravitational pull will not uh, change anything. It doesn't matter. Um, so the black hole can devour or eat the matter only when gets very close to it. Um, so although it's possible that if the whole our galaxy goes very close to the Sagittarius A, it can swallow, but usually it doesn't happen. There's another reason also. The other reason is that uh, matter has uh, angular momentum also. The planets, stars, everything revolves around the central particles, right? Because the planets move around galaxy, our stars, and the stars move around galaxies. So what it means is they have angular momentum, and if you go to closer and closer to by some way you can go to the closer and closer to the center of the galaxy, your centripetal force also increases. What that means is you don't want to get further closer to the center. So that's what it means. So therefore, yeah, of course, if you get closer to the black hole, everything, it can swallow everything. But in principle, In real, that doesn't happen because uh, it's not easy for the things to get close to the black hole. Okay. um, so then we can talk about uh, the supermassive black hole, which are detected in the early universe. Um, you know that the farther you look away from us, and the you go back in time. So sky is kind of time machine, or looking through is some kind of time machine, because you go very very back in past. Um, so the James Webb Telescope is it can see very far in the space. That means very back in time. So we see that there are galaxies which are after 1 billion years after the Big Bang. Uh, what that means is that there were supermassive galaxies, supermassive black holes, uh, in after a billion years of Big Bang, which is too soon, because according to our current ideas, it takes time to merge galaxies, merge, and to become supermassive black holes. Because remember again, how the galaxies grow. There are, like stars, galaxies are also live in binary systems. After a long 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 time, they merge to each other, and the central black hole becomes bigger. You may know that one day uh, Milky Way galaxy and Andromeda, with both college, meaning they also will um, become one. But that's billions and billions of years after. So the idea is that it takes a long time uh, uh, to merge for galaxy merge and to grow black hole. Now the question is that how does the galaxies supermassive form after a short time, like a billion years ago, because it takes a long time to form a supermassive black hole. This is one of these ideas, and some of the solution ideas is that something called black hole stars. So, which are the stars powered by black hole at the center? They are massive, massive, million times bigger than the sun, and these are powered by the black holes. And if there are this kind of stars, these are not galaxies. These are stars millions times bigger than the sun, and if they and it's easier for them to collide and to become to merge and to become one, and then they may become uh, supermassive black holes. That's the one of the proposed solution for the challenge, is that how are supermassive black hole formed early in the universe. Um, and the third kind, there are other kinds of black hole also, which is primordial black holes, which are called. The primordial black holes are the ones which actually are not like stellar black hole or supermassive black hole. These are formed at the right after the Big Bang. Uh, so the idea is that after Big Bang, there were density fluctuations, right? There were dark matter and all the things. So there were tiny fluctuation in the density of the universe, and it might happen that there was really really over dense regions which could potentially squeeze to become black holes. And so these are could be these are called primordial black holes, and they could be everywhere because they were formed at the beginning of the universe. And there have been a lot of work going on this, and they could be very tiny and they're very big. The sizes, the predicted size has a large range, uh, and but although these are theoretical predictions, and the theory been working out, uh, that there are no observational detection of primordial black holes. Um, so these are the basic kinds of black hole: the stellar black hole, supermassive black hole, and uh, uh, primordial black holes. Are there any questions? If there are any questions? Okay. Um, I think I basically described the three types of black holes and their evolution, how they are formed. Um, so if there are no questions, maybe see you next time. Okay, we'll see in other sessions of live. Thank you for joining. Okay, this. Okay, thank you. So Panar is thank you, Gopal. Thank you, Panar. But there's a question: since it's believed that Big Bang originated from singularity, is there a chance for the singularity in the black hole to cause Big Bang? Since it is believed that the Big Bang originated from singularity, yes, correct. Is there a chance for the singularity in the black hole to cause Big Bang? Well, this is slightly different ideas. So so there's a qualitative difference between the black hole and the Big Bang. The black hole swallows things. Yes, it sucks into it everything that goes into it. But on the other hand, the the Big Bang is things came out from the Big Bang. So this is the opposite case. Yes, some kind of, so people say it's some kind of Big Bang is actually some kind of white hole, because in black hole everything goes in, uh, in white hole everything will come out. So that's the idea, and it's possible that it is actually, but the nature of singularity could be the same, but this is active field of research, so people are still working on it. I hope that answers your questions. All right. So thank you for joining. Uh, um, thank you. I'll see you in next live season. Bye bye.